All right. This video will be discussing second order circuits, RLC in series and underdamped. So let's begin by looking at our problem. Our problem can be found right here. As you can see, it has a 20-volt source with a switch that closes at T is equal to 0, two resistors in parallel, an inductor, and a capacitor. The goal of this problem is to find V naught of t for t greater than 0, meaning we want to find the complete response for the voltage over the capacitor. So, where do we start? Well, we are going to be using these steps to solve the problem, and we're going to start at this point here with table 9.1. So, I am sure Dr. Peak by this point has shown you this table, and it is very important for you to memorize. These are all the relevant equations that you'll be using to solve RLC circuits going forward with the class. And while I understand that you might not have it memorized at this point, you should strive with every problem to continue to memorize this table. So we will be referencing this table as we move forward to solve the problem. Next, we will actually follow these 7 steps to solve the RLC circuits presented to us. And we are going to start with step 1. Step 1 involves writing that our VC0 minus is equal to VC0 plus, IL0 minus is equal to IL0 plus, and I of C over C is equal to dVC dt. So that is exactly where we started. The reason that we write these down is that we will use these relationships to further down in our problem to continue to solve. Our IC of C is equal to dVC dt. It looks a little different, but really it's just our relationship of current through the capacitor to the change in voltage of the capacitor. You probably have seen it as IC is equal to C dVC dt. But moving forward, let's go on to step 2. Step 2 will be determining our initial conditions. We'll be doing this by drawing our circuit for t less than 0, t greater than 0, and for t infinity. All right, let's start this out. Our circuit at t less than 0, we will have our 20-volt source with our switch open as it closes at t is equal to 0. We'll have our 2 resistors in parallel, our inductor, and our capacitor. Well, if we look at this, we notice that there's no current flowing through the circuit. Therefore, there is no charge having built up on this capacitor, meaning that we can say that our VC of 0 minus is equal to 0 volts. We can also say, since there's no current flowing through the circuit, that our IL of 0 minus, there is no current flowing through our inductor. Therefore, IL of 0 minus is equal to 0 amps. If we move down and we now draw our circuit for t greater than 0, we see that the switch has closed. At that point, you would see the same circuit with the switch closed. Our 20-volt source, our 2 resistors in parallel, our inductor, and our capacitor. Well, at this point, we wrote down the relationship up here. What we see is that VC0 minus is equal to VC0 plus. Well, the reason for this is because at that instantaneous moment that the switch closes for t greater than 0, it has not been enough time for the components to react yet. Therefore, we can say that the voltage over our capacitor, the current through our inductor, is the same as our steady state before that. So saying that, we can see that VC0 minus is equal to 0 volts. Therefore, VC0 plus is equal to 0 volts. Same goes for IL0 minus is equal to 0 amps. IL0 plus is also equal to 0 amps. Moving forward, we will draw our last circuit here, which is at time equal to infinity. This would include our 20-volt source, our 2 resistors in parallel. Our inductor at this point will begin to act as a wire, and our capacitor will act as an open. The reason for this is that our capacitor is now fully charged. Therefore, it is going to inhibit DC flow. All right, with that drawn, that leads into step 3. Our step 3 is going to be determine final conditions, which are going to be our equivalent resistance, our voltage over the capacitor, and our current through the inductor at t is equal to infinity. Okay, well, considering this circuit, or considering our capacitors acting as an open, there is no current flowing in this circuit. Again, therefore, there will be no current flowing through our inductor. So we can say that the current flowing through our inductor at t is equal to infinity is equal to 0 amps. But for our capacitor, the only reason it's acting as an open circuit at t is equal to infinity is because it is now fully charged. Therefore, it has a voltage of 20 volts, which we'll also call or say is equal to our V of F. Our equivalent resistance at this point is going to be 450 ohm resistor in parallel with the 900 ohm resistor. This comes out to 450 times 900 over 450 plus 900, which comes out to an equivalent resistance of 300 ohms. With our initial conditions determined, let's move on to step 4. Step 4 says calculate the alpha and the omega naught, then use these to determine whether the circuit is underdamped, overdamped, or critically damped. Well, as you know, this circuit will be underdamped, but let's just do the calculations to confirm that this is the case. We will go back and reference our table 9.1. As you can see here, alpha and omega, whether it's overdamped, critically damped, or underdamped, they are found the same way. They are always determined using these equations. Well, this is going to be a circuit that's in series. So our alpha is going to be equal to R over 2L, which in this case will be our R equivalent. And omega naught is going to be equal to 1 over the square root of LC. All right, let's go back and do that then. So we are in series, as we've determined. Therefore, our alpha is equal to R equivalent over 2L, which is going to be equal to 300 over 2 times 0.4 e minus 3. This just means 0.4 times 10 to the negative 3, just a shorthand way of writing it. In this case, this comes out to our alpha is equal to 375,000 rads per second. All right, well, going back to table 9.1, our omega naught is going to be 1 over the square root of LC. So 1 over the square root of LC is equal to 1 over the square root of 0.4 e minus 3 and 10 e minus 9, as this is nanofarads. Solving, this comes out to our omega naught is equal to 500,000 rads per second. All right, well, let's look at this. Our alpha is less than omega 1, which as we can see here in our table 9.1 means that our circuit is in fact underdamped. All right, looks good. At this point, we should go back and we see that we need to use this now to form an approximate natural response. What's important here is when there are no sources attached, the circuit will have only its natural response. Therefore, looking back at this table, this response right here will be our natural response, which is e to the negative alpha t times b1 cosine omega dt plus b2 sine omega dt. Well, our omega d also has to equal the square root of omega naught squared minus alpha squared. All right, well, let's write that down then. We will write that down as this is our natural response with omega d equal to omega naught squared minus alpha squared, the square root of that. All right, well, we have our omega and we have our alpha. Plug them in here, we get that omega d comes out to 718.9 rads per second. All right, well, we need to remember that this right here is just the natural response found on table 9.1. This leads us into our step 5. Step 5 is find B1 by evaluating the complete response at t is equal to 0. Where, as I mentioned before, the complete response or the natural response is what was given to us. The complete response is going to be our forced plus our natural response, which in this case is going to be our VF, which we can see up here that we listed as 20 volts. So our complete response comes out to 20 volts plus our natural response. Well, okay. We will be completing or we'll be evaluating this complete response at t is equal to 0 in order to find B1. So if we plug in 0 to this complete response here, we are going to get 20 volts plus e to the negative alpha 0, so this is going to go to 1, b1 cosine omega d 0, which means this cosine of 0 is going to go to 1, plus b2 sine omega d 0. Sine of 0 is going to go to 0. Therefore, we are left with 1b1. This then comes out to v naught of 0, which is our complete response, is equal to 20 volts plus b1, meaning that we can now solve for v1 is equal to negative 20 volts. All right. This takes us to step number 6. Step number 6, find b2 by evaluating the derivative of the response at t is equal to 0. All right, so here's our complete response. If we take the derivative of this, this would force this to go to 0, or this would go to 0. And we would be left with taking the derivative of the natural response here. Well, you should, and I highly recommend, going back and refreshing yourself on the chain rule, because that is what is occurring in order to take the derivative of this natural response. When you do that, you come down to this point, you get dv dt is equal to e to the negative alpha t times negative alpha b1 cosine omega dt plus alpha b2 sine omega dt minus omega d times b1 times sine omega dt plus omega d times b2 cosine omega dt. I highly recommend you practice working this derivative out again. Go review the chain rule. At this point now, we need to evaluate the response at t equals 0. So after having taken the derivative, we are going to evaluate it at t is equal to 0, meaning that it comes out to e negative alpha of 0, which will just go to 1, minus alpha b1 plus omega d b2. Okay, well, we have alpha, we have omega d, we have b1. All that's left is this dv naught of 0 dt. Well, if we scroll back up here, v naught is just going to be our voltage over the capacitor. So coming back down here, or looking back here at step 1, I had you write down the relationship. IC over C is equal to dvc dt. If we take that relationship and apply it down at this point, we can say IC over C is equal to dvc dt. Well, our IC at time is equal to 0, or in this case 0 minus or 0 plus at this point, we know that to be equal to 0. That's what we found up here at this point. The current coming through at time less than 0, or at our IC of 0 minus is going to be 0. Okay, with that being the case, we get 0 over 10 nanofarads is equal to dv naught of 0 dt, meaning that this goes to 0 as well. So as this goes to 0, we plug in our alpha and our b1 and our omega d, and we solve for b2, and it comes out to b2 is equal to negative 22.6779. Well, with that, we have our complete response. Coming back up to this point is going to be our forced plus our natural response, and we just now have to plug everything in. So our forced is going to be 20 volts. We are going to have that plus b1, but b1 is equal to negative 20 volts, so it's going to come out to minus 20 e to the negative 375,000 t, this being our alpha, times cosine 330,718.9, which is our omega d t. We then again would have plus b2, but b2 is negative, so we'd have minus 22.6779 e to the negative 375,000 t, again this is our alpha, times sine 330,718.9 t, this again being our omega d. And that is the complete response, and that is our final answer.